Okay, so today we are going to be talking about continuity and one-sided limits. One of our learning goals here, we want to be able to find the value of a one-sided limit, and we want to be able to identify the type of continuity. Here's the formal definition of continuity at a point C. A function f of x is continuous at point C if the following are true. If f of c is defined, if the limit as x approaches c of the function exists, if the limit of f of x as x approaches c is equal to f of c. All that's saying is that we need to have a y value. We need to have a limit at the specific x value we're looking at. And that limit has to be equal to the y value. When all of that happens, that means we have a continuous function at that point C. The limit of f of x as x approaches c is going to be L if and only if the right-hand limit as x approaches c and the left-hand limit as x approaches c both equal L. In limit notation, this is the way it would look. The limit of f of x as x approaches c from the positive side must equal the limit of f of x as x approaches c from the negative side. If those both are equal, then we have a limit that we call L. If we have a continuous function, to find that limit, we're simply going to plug the c value into the function. A function can be what? Well, it can be continuous, or it can be discontinuous. Need another U in there. If a function is discontinuous, we can have two types of discontinuities. The discontinuity can be removable, or it can be non-removable. Down here we're going to look at some types of continuity. Looking at graph 1, we have a big gap right here. Even if I were to fill in this point, it's still not going to be continuous. This is what we call a non-removable discontinuity. Instead of writing that over and over, we're going to get an abbreviation for that. We're going to call it NRD. Non-removable discontinuity. Look at graph 2. As I come in from the left and I come in from the right, the limits are not the same. They are both going to infinity, but that is not a specific number. So therefore, here, because it fails this test, and because f of c right here, or f of a in this case, because f of a is not defined, there's another reason that we have a non-removable discontinuity. On this function, as I approach a from the left and as I approach a from the right, I'm approaching the same L value. Therefore, this does have a limit. However, in order to be continuous, f of c must be defined. We have to have a y value there, and we don't. So therefore, this would be called a removable discontinuity. And this will have a limit, like I said. The reason this is called a removable discontinuity is because I can remove the discontinuity so easily. All I have to do is fill in that dot, and then it will be continuous. Graph 4. This is another example of a removable discontinuity. The reason it's a removable discontinuity is because I could literally pick up this dot, put it there, and then it would be continuous. Graph 5. This is going to be a continuous function. You can either write it out, or you can just put C for continuous. The reason it's continuous is because I can trace over top of it without lifting my pen. As we approach A from both the left and the right, we're approaching a specific Y value. So we have a limit, and the limit is equal to the y value, therefore it's continuous. In this one, we do have a specific value for y, but that value for y is not the same as the limit is, so therefore it's a removable discontinuity. So that's graphically explaining continuity. Let's look at an example of continuity algebraically. In this problem, I have this graph, and we actually have a graph of it for you. There's one thing you can't see though, and that is if I cancel these two out, I am left with the function y equals 3x. That's what this graph is right here. So what there really is because these canceled, there's going to be a hole in the graph at 1 comma, when I plug 1 in here, I'm going to get 3. So at 1, 3, there's a tiny hole in the graph right there. And this is the way the graph looks. The limit as x approaches 1 from the left side, you can see that's 3. The limit as we approach 1 from the right side, you can see that's 3. So we do have a general limit. These are one-sided, this is general. As long as these match, we have a general limit. However, f of 1 is undefined. We don't have a point there. Does the limit as x approaches 1 equal f of 1? No. Discuss the continuity of the function. There's a tiny hole in the graph. If I fill that in, then it would be continuous. That's called a removable discontinuity. What is the limit of f of x as x approaches negative 1? Here's negative 1. As I approach negative 1, that limit is negative 3. All right, let's go on to the next part. All right, this is what we call a piecewise function. We're graphing x squared plus 2 as long as x is less than or equal to 2. So we have this parabola. If I plug 2 in here, 2 squared is 4 plus 2 is 6. So at 2, 6, I've got this closed dot. There's the way that part of the graph looks. We've got y equals negative 3. That's down here. If I plug 2 in here, I get negative 3. But that would just have to be an open dot, because I'm not actually equal to negative 3 there. But I have to put it there because of 2.1, 2.2, 2.01 limits. The limit as we approach 2 from the negative side is 6. The limit as we approach 2 from the positive side is negative 3. The general limit. These one-sided limits must be the same in order to have a general limit. They're not, so the limit does not exist. G of 2. That means what is y when x is 2? Looking at 2, there's the closed dot, so y is 6. What is the limit as x approaches 0? We can see that, 2. What is g of 0? 2. Is g of 1, right here, equal to the limit? Well, yeah, they're both going to be 3 in that case. So yes, they're both going to be 3. Look at it again. Here's 1. The y value is going to be 3. As I approach it, it's also 3. Is g of 2, here's g of 2, equal to the limit as x approaches 2? No. Because we had an answer for g of 2, it was 6, but the limit did not exist, so they do not match. Alright, that's it for the first part of 1.4.